This is section 3.4, number 3. This has to do with our derivative test. We're going to be using the second derivative test, the first derivative test if we need to. We only need to use that if the second derivative test fails. We're also going to look at the concavity test. This is going to help us to sketch the graphs of polynomial functions. So the example, for the function, find the relative extrema using the second derivative test if possible. State the coordinates of the points of inflection, find the intercepts, and sketch the graph. All right, so the first thing we can look for are the intercepts. So if I plug in 0 for x, I'm going to get -3 for y. So 0, -3, we've got that. Let's go ahead and find the y-intercepts. We plug, x-intercepts. Plug in 0 for y. Solve for x. Well, that's going to be 1, 0, and 3, 0. Okay, so at this point we're going to find any extrema that we might have. So I'm going to take my first derivative. I'm going to do derivative of the first times the second plus the first derivative of the second. In order to set this equal to 0, I'm going to have to factor out an x minus 1. I'm left with the 2 times x minus 3 plus x minus 1. That gives me x minus 1, 2x minus 6 plus x minus 1. So I have x minus 1 times 3x minus 7. I set that equal to 0. That's going to tell me my critical numbers. So 1 is a critical number and 7/3 is a critical number. So to do my second derivative test, I now find the second derivative. So I'm going to take the simplified version right here, and I'm going to take the second derivative. Still going to use the product rule, or I could even multiply it out. So I'm going to do derivative of the first, which is 1, times the second, plus the first. Derivative of the second is 3. Okay, so now I'm going to have to multiply this out at this point. So I'm going to have 3x minus 7 plus 3x minus 3. That gives me 6x minus 10. Okay, so that's going to be my second derivative. I'm also going to have to find my points of inflection, so I'm going to set this equal to 0. And that's going to give me 10/6, which is 5/3. So that's going to be a possible point of inflection. All right, so we're going to use our second derivative test. This is where we plug in the exact numbers that we got for our critical numbers. So I'm going to plug in 1 and I'm going to plug in 7/3. And I'm going to plug those into my second derivative right here. So I'm going to have 6 times 1 minus 10, that's negative. So what that tells me is the graph is concave down and the slope is 0 right there. So therefore this is going to have to be a max. When I plug in 7/3, 6 times 7/3 is 42/3. That's greater than 10, so if I subtract 10, I'm going to get a positive number. So I have to be concave up. At that point, I'm going to have a minimum. All right, so I might as well find out what these exact points are. So if I plug 1 in, I know I get 0. I might as well plug in 7/3. So if I plug in 7/3, 7/3 minus 1, that's going to be 7/3 minus 3/3, that's 4/3. If I square 4/3, that's 16/9. And then plugging 7/3 in here, 7/3 minus 9/3 is going to be -2/3. And so that's going to give me -32/27. Okay, so that's going to be a minimum. And then I know I have a max at 1, 0. Okay, so now we're going to find our concavity to see if we have any points of inflection. This is where we use intervals. We're going to go from -infinity to 5/3, and from 5/3 to infinity. I'm going to check 1, I'm going to check 2 or 3, just check 3. Plugging these into my second derivative, if I plug in 1, I'm going to get a negative value, so we're concave down. If we plug in 3, we're going to get a positive, so we're concave up. So that proves then that 5/3 is going to be a point of inflection. Plugging 5/3 back in, 5/3 minus 1, that's going to be 2/3. 2/3 squared, that's going to be 4/9. And then 5/3 minus 3, 5/3 minus 9/3 is going to be -4/3. So that's going to give me -16/27. You can also just grab a calculator to get those values. All right, so anyway, putting all this together, we're going to now have our 7/3, that's going to be 2 1/3, and then this point is a little more than -1, a little smaller rather. So we're going to be right about there for a minimum. and I have my maximum at 1, 0. I have my point of inflection right here at 1 2/3, negative 16 over 27, right about in there. Now this I know has a degree of 3. So if it has a degree of 3, it has to have opposite end behavior. It has to go down and then up. So here's the way I know my function's going to have to go. This has to be a max. I had to be concave down until I got to this point of concavity, point of inflection. Then I'm going to switch to being concave up, and so that's the way our function's going to have to look. So if we wanted to check that, we could put it back into our original function just to check our points and things. We just don't want to have to use the calculator to find all of this. Here we go. And so I'm just going to check some of these points just to make sure I did that arithmetic correctly. I did it kind of quickly. 7/3 gives us that number. Let me see if that's the same as negative 32 over 27. Yep. Okay, and then we had to do second trace calculate 5/3, and that's 0.59, etc. Negative, okay. And that's the same thing too. And so therefore we know that the minimum, maximum, and the point of inflection are correct.